Okay, I guess we'll have to edit some of this. It's fine. All right, everybody. Welcome to Solutions and Solubility. So, on Classroom, we had an assignment to watch a video and answer the quiz. Now, if you didn't quite get the information from the video, well, let's go over some of it for you guys um, right now. So if you go to classwork for Thursday, Friday of this week, 423, 424, I posted the solubility instructions. This assignment is, just watch the video. You don't have to turn it in if you don't want. And then, of course, there's the quiz from quizzes. You probably got that sent directly to you um, because if you join the class, it sent it right to you. So that's how that works. So if you're having trouble doing the quizzes from the video, well, you can watch this video and you can answer it as well. And remember, you can always go back and retake the quiz up until today. I'll probably change the due date. Oh, I did. I changed it to like April 30th. So yeah, you're good. All right. So anyway, let's talk about solubility solutions and what's it all about. So in the previous chapters, we were talking about gases. And we talked about how gases needed to be described in terms of their pressure, temperature, volume, and amount. Well, that's great. We were able to do all kinds of cool stuff with that. Um, but what about solids and liquids? Well, if they're pure, then all we need is the mass. What is the mass of this stuff? Boom, now we have moles. What is the mass of this stuff? Boom, now we have moles. Well, what if we didn't have the ability to find the mass, but it was still a pure substance? Then we could just simply go, okay, what's the volume? Because if we have the density, then we could find the volume and thus find the mass and thus find the moles. But in the case of most things on this planet, if you look at the Earth is covered in water. And if you guys know, water is full of what? It's full of salt. So if we zoom out on our beautiful blue dot, it looks like there's nothing but land for the eye can see. But if you notice, if we zoom out, then we have just salt water everywhere. Big old ball of salt water. And if I zoom out further, sometimes it'll switch. No. All right. So how do you do like a reaction with salt water? Is it the water? Is it the salt? How do you measure them? How do you know how much salt is in there versus the water? And this is the idea behind solubility. So whenever we talk about any sort of mixture, we usually talk about the thing that is being mixed into the other thing. One of the things is mixing into one of the other things. So in the case of the salt water, there's way more water than there is salt, and we say that the salt is being mixed into the water. And more specifically, we say that the salt is dissolving in the water. So we call that the solute. And then for the thing that is doing the dissolving, we call that the solvent. Solute is kind of a fun word to say, but that's the idea. If we have a mixture of something that it's usually a liquid mixture, we call that a solution when the solute dissolves in the solvent. So what does it mean to dissolve? Well, let's take a look. When you are dissolving, here we have a salt shaker and we have some water. When you are dissolving, you are being completely encapsulated by the water molecules. As you can see, when the salt, in this case this is sodium chloride, goes into the water, it splits up. The salt, the sodium ions and the chlorine ions seem to break apart and they seem to float around. But what's actually happening inside there? Well, if you remember from the video, the link takes you to this page. And this page plays the video, sure, but they have a very good animation. Is it this one? Yeah. So this one is a very good animation of what exactly...
When the salt comes in contact with water, the positive sodium ions can become surrounded by the negative oxygen ends of the water molecules. And the negatively charged chloride ions become surrounded by the positive ends of the water molecules. And the separate sodium and chloride ions can then diffuse throughout the entire volume of water, distributing themselves evenly. When all of the molecules are dispersed in solution, it is the perfect environment for a beautiful reaction to take place.
All right. So, as you can see, the water molecules want to stick to the salt particles. In this case, the sodium ions, the positive sodium ions, and then the negative chlorine ions. The water wants to stick to them because the water acts like a little magnet with a positive end and a negative end because of its polarity. So what it means to dissolve, for it to disappear into the solution, is for the water to encapsulate it inside there. This same thing happens with sugar. It's just it doesn't get split up into its individual particles. Sugar just stays sugar. But it's the same idea. The water molecules wrap around it completely, just like they do here in the video. With the individual ions, the water molecules wrap around it completely, but the molecule stays whole. But that means there's a problem. The problem is that some things will dissolve and some things won't. We call this soluble and insoluble. So if you take salt and you put it in water, the salt dissolves. But if you take sand and put it in water, it doesn't dissolve at all. Then we have another idea which is called miscible versus immiscible. Miscible means it has the ability to mix together, and immiscible means it cannot be mixed together at all. And so the best example of this is oil and water. So if you've ever had like vinaigrette salad dressing, then you've seen, oil and water demonstrations where they just won't mix together. Now, in class, I would have had a really cool demonstration. You guys would have walked around and played with that. But the oil, in the case of the vinaigrette in your salad dressing is olive oil. And then the water solution is usually vinegar. That's why it's called like a vinaigrette. The vinegar is dissolved in the water. It's a salt that dissolves in the water, but the oil can't dissolve in the water, but on top of that, what it also can't do is it can't mix. And the reason for that is what we call like dissolves like. And so the idea is that the polarity of the molecule, whether it's polar or non-polar, will result in something being able to dissolve it. So let me show you what I mean. Let's look at some molecules here. We'll look at water, and we'll look at a typical oil molecule. So if we look at water, water is an oxygen molecule. Sorry, oxygen atom, and it's in this bent configuration with two hydrogen atoms It has two lone pairs of electrons up here. And what this means is that if we look at the electronegativity difference between the hydrogen at 2.1 and the oxygen at 3.5, that is an electronegativity difference that is so great enough to cause the electrons to want to move towards the oxygen. And so in essence, what this looks like is a big old bubble right here. We have two big old bubbles right here. But the bubbles are acting in a positive way, and the black bubbles are acting in a positive way, and the red bubble there is acting in a negative way because of that pull towards that towards the oxygen. So what this gives us is kind of a big old region of negative area and a big old region of positive area. And so because we have two opposite sides, we call this polar. And so the water molecule is polar, and it will dissolve any other object that it can stick to, just like a magnet would with a north and south side. It will try and dissolve anything that it can stick to. Well, if we compare that to carbon and hydrogen in a fat like an oil, you get these big long chains, and there's some stuff going on here at the end, and there's a thing that sticks off here, but we're going to ignore that for now. We're just going to look at the hydrogen. So we're going to have a hydrogen that's kind of sticking out here and sticking out there and sticking out here, sticking out there. These hydrogens are just like the hydrogens in oxygen. They have a polarity. Okay, it's still the 2.1, but carbon's polarity is 2.5, which is ever so slightly going to pull the electron density towards the carbon. However, if we look at the whole molecule, this is going to put then all the positives out here and all the positives down here, and all those negatives will be in the middle. And that isn't polar because there aren't two opposite sides. It just kind of all behaves like one kind of homogeneous charge there, because it's all kind of distributed in these very indistinct areas. And of course, this is a very large molecule, so the molecule can like wrap around on itself and then cause even more issues. So this is what we call nonpolar. A great example is if we just look at one, like if we look at methane. If we just look at one methane, here we'll draw it like the shape shows. If we just look at one methane, we have that same issue where we have the electron density wanting to move towards the carbon, but that means we're going to have plus, 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 completely surrounding the carbon with the negative in the middle. There's no way for that to have two opposite charges and behave like a magnet. And so these are nonpolar molecules. And in the case of immiscible, that means that they cannot mix together. They don't have any way of interacting, and so they'll sit on top of each other. Just like if you took one piece of Lego and you put it on another piece of Lego, they're solid and they're not going to mix together, they're just going to sit on top of each other. And that's what's happening here. And then if you wanted to, you could do what's called an emulsion, where you could whip that together and kind of make the little bubbles so small that they don't have the energy to push each other around. And that's what we get when we make things like mayonnaise and other such condiments. So that's called immiscible. So in the case of a polar solvent, it will dissolve polar molecules. A nonpolar solvent will dissolve nonpolar molecules. This is why when you get something like ink or something on your close, they'll tell you to use a different solvent to try and wash it up than soap and water. Sometimes the water won't do anything. Sometimes adding the soap, which is a nonpolar solvent, to help the water dissolve. The most of the soap is nonpolar. There's a small part that's polar, so it can dissolve the nonpolar things, and then it can also interact with the water. Those things don't work, so sometimes you'll have to go to like a full-blown nonpolar solvent, like something like acetone, and then it will actually clean it off. All right, so getting to the stuff that was on the quiz, we have saturation. So what's saturation? Well, let's go back to our little demonstration. If I keep adding salt, that means that there needs to be water molecules to come in and split up those sodium and chlorine ions. Well, eventually, all of the water molecules are going to be used. They're going to do their job at splitting them up, and then eventually they won't be able to split them up anymore. And when this happens, we get the salt to stay as a crystal. There it goes. So as you can see, we have reached saturation. Those salt molecules that are down here in the solution, they are being dissolved on the outside, but those ones on the middle, they're not getting touched by water, and so therefore they can't be dissolved. And if I add any more, because I'm at the saturation point, it will not dissolve at all. It'll sit there and split up and then instantly go back onto this crystal. As you can see, it stays solid for a little bit, but then just falls down to the bottom of the container. Now, salt is fairly soluble, but if we went to salt that is not very soluble at all, we have some strontium phosphate. As you can see, a little bit went in there just fine, but the second crystal, or third, I think it was 4 crystals when I tried this earlier, yeah. As you can see, it doesn't want to dissolve, and so it's going to sit there and it's going to come to an equilibrium, which we'll talk about later in the year, which basically has the strontium and phosphate molecules popping in and out onto this this structure down here. And what's happening is, you notice the shape when it came out versus what's going on inside. What's happening inside is what we call crystallization. The strontium and phosphate in the water is able to arrange itself in what its preferred configuration is, which is this cool like hexagon configuration. And that's called crystallization. I'll have a activity for you guys to do where you get to make your own crystals. So as you can see, we reached the saturation point very quickly. So what are some things that we can do to change saturation? So saturation just means that you're at the limit of the amount of solute that can fit in the solvent. Unsaturated means you're not at that limit. And supersaturated means you've done something to force more into the solution than could normally fit. And we'll talk about what you can do to do that. So first off, what is the measure of solubility? So it depends on the particular thing you're looking up. But typically, when we're just looking at solubility, we're going to describe it in terms of the grams of the solute per 100 grams of the solvent. So for instance, salt at room temperature has about a 33, I think. Let me see. There's salt. So at room temperature, which is about 25 degrees C, yeah, it's about 34, 35 grams of salt per 100 grams of solvent. That's what this table shows. This right here is what we call a solubility curve, and it shows you what happens when you change the temperature on a solvent. So that's how we would get a super soluble solution, is we could heat it up. So anyway, that's how we would measure and talk about the different types of solubilities. So when you're looking at this graph, what you're looking at is anything that is below the line. So anything that is below this line is what we call unsaturated, and everything above the line is supersaturated. So this is unsaturated, and this is supersaturated. So if you're able to force 40 grams of salt into the water at room temperature, you have what's called a supersaturated solution. And as soon as you stop doing that thing that is forcing the salt in there, it will start to crystallize. So, when you guys are doing your quiz and they're telling you to read this graph, that's pretty much all you're doing is you're looking at it and saying, okay, are we above this line? Are we below this line? Saturated, unsaturated, um, and then of course supersaturated. We would have done a lab with the potassium nitrate here, where we would have taken potassium nitrate and heated it up, and then we would make this curve from our data. It's in your homework packet, but potassium nitrate, not something you want to play with at home, so I'm not going to make that an at-home lab. You could get it, but not advisable. So what are some things that affect solubility? How can you change solubility? So when it comes to gases, because they are susceptible to pressure, you can use pressure to force gases into a solvent. So in this case, that means if you increase the pressure, you can increase the solubility. So if we type in solubility curve for gases versus the one I showed you, which is this is for solids. These are all solids. You'll notice that most of them have what we call a positive slope, which means that if you increase the temperature, it increases the solubility. Well, for gases, they don't like temperature. And one of the other things that we can use to increase solubility is temperature. And the reason why this works is because basically you're getting the water molecules or whatever solvent molecules to move a lot more. And because they are moving a lot more, you can see there's a degree of movement in here. Because they are moving a lot more, they are able to bump into the little molecules of the salt more often and more likely result in a dissociation between this, in this case, the strontium and the phosphate. But then that strontium and phosphate can then bump into the crystal there and redeposit itself. And so if you let that sit for a while, you'll see it turn into a bunch of cool little hexagons over time. Crystallization occurs. So temperature makes solubility go up for solids and liquids, but it actually makes the gases go down. And that is because gases need pressure to be dissolved into the solvent. And if you heat things up, you make more room for them, and that means they can just float away, as you can see when we look at the solubility. Now, I want to show you the difference here. Notice the solubility is in what's called millimoles there, but we want to see, here we go. Here is the same solubility in terms of 100 grams of solvent, but now they notice they wrote milligrams. This isn't even on the same scale. If we were to look at the scale here, the milligrams would be down here. The whole graph we're looking at is a tiny little circle that's happening right down there of these particular gases. So if you look at oxygen in water, as you guys know, oxygen is what we breathe. We can't breathe it out of the water because the speed at which it is and the amount of which it's in the water is not enough for us. But say you have a fish, it's breathing oxygen. Well, that 7 at 0 degrees C, we have, notice the lower temperature, we have 7 milligrams per 100 grams of solvent. But as soon as we get to room temperature, we've gone down to 4. So there's a lot less oxygen in the water as the temperature increases. And eventually you'll have gotten the temperature so hot that it just can't hold the water at all. So those are the two main factors when it comes to solubility: temperature and pressure. Pressure only affects gases, and temperature affects everything, solids and liquids positively, gases negatively. Now, what's another thing that is important for solubility? And that's surface area. So you'll notice that these numbers are really tiny, and that's because we are zoomed up on this water. We are looking at like a very tiny drop of water. If we wanted to make some solution of say Kool-Aid or any of that other stuff, what does it come as? It doesn't come as a cube. It comes as a powder. And what we're doing there is we're increasing the surface area. When you increase the surface area, I wanted to type in Kool-Aid, but it doesn't matter. If you want to look at the surface area, that's where the water can actually bump into the molecules. So as you can see, if we look at the crystal here, you'll notice that the dissolving, where the little purple and green balls are coming and going, is happening on the edges of the crystal. And so the smaller the crystal, the more the water can interact with those things. So higher surface area will result in greater solubility. But this really only affects solids because liquids have basically infinite surface area because they are completely being able to be moved around, and gases are the same way. But for solids, they are able to shield the inner parts of them so they don't dissolve. And if you look at things like rusting of your pipes, the pipes rust where the water touches the pipe. It doesn't rust in the middle of the pipe. It rusts where the water touches it. So, I hope that was able to help you a little bit with your information on your quiz. Because again, that's pretty much what it's asking you is about solubility, dissolution, so the ability to dissolve in a solution is based off its polarity. Polar dissolves polar, nonpolar dissolves nonpolar. And so what's going on here with this selenium sulfate here is you'll notice it doesn't want to really dissolve in the water at all. And so some things just don't have a very good solubility. And the reason for that is their attraction to each other is just way stronger than the water's attraction to them, and they can't pull it apart. And again, if you think about it like magnets, some magnets are stronger than others. These two magnets are super strong, and they just don't want to attract anything else, and so they don't split up. So that's solubility in a nutshell. I hope that helped.